Okay, what we have here is a disc. It's a solid disc, and it has a radius of 0.2 meters, and it has a mass of 40 kilograms. And someone has applied a force that's tangent to the disc, and it's 30 newtons. The question that we're trying to find is, what is the velocity, the tangential velocity, and then I want to know what speed. I want to know like the magnitude of the acceleration. So like so not the angular, but like the linear, the linear acceleration. Okay, we'll get into those in a second. Now, and we want to find those. So this thing is initially at rest. So it's v0 is 0. Just go back. 0 meters per second. So it started at rest, meaning it's not spinning at all. And then it's going to spin for 0.2 revolutions. So it's going to spin for 0.2 revolutions. And at that time, I want to know what's its velocity. So obviously, its velocity is going to continue to increase so the acceleration is constant. You're like, how do you know the acceleration is constant? Because there's a constant force. If the force is constant, then the acceleration is constant, right? Because forces and acceleration are directly related to each other, right? F equals ma. So if the force is constant, acceleration is constant. Okay, so if there's constant acceleration, then that means the velocity is going to continue to go up and up and up and up and up and up and up. And so, but what I want to know is, what is it at after this thing is spun around for 0.2 revolutions, or 20% of a revolution, right? So it hasn't gone very far. So okay, so let's do that. Now, this is a circle or a wheel, and so normally if you're doing linear things that are moving linearly or translationally, if you will, then you would use the formula F equals ma, right? Force is equal to mass times acceleration. That's Newton's second law. But that's for things that are moving, like I said, transition from like left to right, or like straight, linear, right? Non-circular motion. But if things are moving in a circular motion, then there's a different formula for it, and it's torque, or tau for torque, is equal to I. I is the moment of inertia. Remember, that's basically how the mass. It's like mass, but how the mass is distributed along some object through its radius. And then there's alpha. Remember, alpha is just like radians per second squared. So whereas A is meters per second squared, alpha is radians per second squared. And then remember, I is like, you're like, I don't remember what I is. Well, we can, maybe I'll just break out these things separately. So tau is torque, right? And so torque is basically force times the distance. So as long as they're at right angles to each other. So if they're not at right angles, then you have to do like vector math. But as long as you can make the two things at 90 degrees to each other, meaning the force and like the lever arm, as long as they're 90 degrees to each other, then you can just multiply them. So this is like the simplified version of it, as long as they're at right angles to each other. And then I is the moment of inertia, and that's basically the integral of, it's the mass times the square of the radius, right? Meaning as the radius gets farther and farther out, it gets worse for the inertia. It gets stronger, if you will, because the radius gets squared, right? Times the mass at that point. So you just like sum up the mass along this radius, and yeah, and that gives you your moment of inertia. And then of course alpha is just radians per second squared, right? And remember, in a circle there are 2 pi radians. So if I'm drawing a circle, right, that's pi, 1 pi, 2 pi, right? 3 pi, 4 pi, 5 pi, 6 pi, okay? So that's kind of how that works if you were in a circle. So here we have these three things. We, of course, know what F equals ma is, and now hopefully have a better idea of tau equals Ia. Great, because this thing up here is moving in a circle, we have to use this second equation and not the first one, right? Because this is circular motion. Okay, so how can we convert F equals ma to tau equals Ia? Well, I need tau first. And so tau is torque. And so remember, torque is just the force times the distance, as long as they're at 90 degrees to each other, right? If they're not at 90 degrees, so let me just give an example. So let's say I had this right here, and the circle represents the pivot point, and the force is pointing straight down like that. Force is pointing straight down. These are at 90 degrees to each other. The arm and the force are at 90 degrees, so therefore you can, whatever the length of this is, it's just L times F, right? That gives you your torque. And typically force is in newtons, and the length is in meters, so you would say the torque is whatever, 50 newton meters. The other way you could do it is, but what if they're not at 90 degrees? Okay. So let's say you have this here, and let's say your force, I don't know, is like that. Let's say your force looks like that. And so your force is not at 90 degrees. Well, all you have to do is just change it, right? All you have to do is do like this, right? You can break your force down, that vector, into its components, right? And then you can figure out, right? You have to figure out what this angle is. Maybe I'll call it, I don't know, beta for some reason. And if you knew beta, let's say you know what your beta, and then the force here is F, right? The force is F. So it's not F. It's gonna be some smaller number than F, right? So it's F times what? Well, in this example here, if you knew beta, it would be cosine, because you're looking for this side, right? You're looking for, let's call this side A and this side B, okay? You're looking for the A vector, right? Because A is 90 degrees. A is 90 degrees, right? So how do you find that side? Well, just F, and because B is close to it, that's adjacent, so you'd say F cosine beta. And that would give you the force at 90 degrees. And so you would take that, and then you'd multiply that times your length, L. Multiply that times your length, L. Okay? And then that would give you your torque. There's another way of doing it, and that's instead of, essentially what I did here is I straightened out the F. Right, the F was at an angle, I just straightened it out, and I made it at 90 degrees. But what if you left the force alone and you straightened out the arm instead? So that's the other way of doing it. Is imagine here, maybe I'll do the same thing like that. And so instead of straightening out the arrow, what you could do is straighten out the arm. So you could say, okay, what I'm going to do is maybe make this arrow long, just so you can see it like that. And then what you do is take this, yeah, and now this is 90 degrees. See that? So you would leave your F alone. So here's my F. It's by itself. And this is still L, right? This is still L. But instead of using that L, we'll call this like L prime. We'll use that L instead, because that is 90 degrees to F. See that? So as long as the force and the lever arm are 90 degrees to each other, perpendicular, then you're fine. So you could either like move F, so to speak, or use this component to make it 90 degrees, or you could like move L to make it 90 degrees. Either way works, okay? And once again, you would just have to do some trigonometry, because L prime is what? L prime is just L, right? And let's say you knew this, let's call this, I don't know, theta. Let's call that theta. Let's say you knew that angle right there was theta. right? So, and because that's adjacent to it, you would say cosine. So it would be L times the cosine of theta, right? So anyway, so that I'm just showing you how to find torque. Torque is just, it's easiest when they're at 90 degrees. If they're not, you just move either the force vector or you could move the lever arm, right? Move either one that you want, as long, and just make them 90 degrees. Okay, because the force here at the top 30 is 30 newtons, and it's tangent to the circle. Let me just change this. Maybe we'll do blue. It's kind of hard how I'm looking at this, but it's essentially at 90 degrees to the pivot point, i.e. the center of the circle or the disc. It's essentially at 90 degrees. So this F and what we call L before are at 90 degrees. You can just multiply them together. So then tau equals, essentially here, force times distance, or your lever arm. The force was 30. And then the distance is just the radius, 0.2. Okay. And so you end up with 6 Newton meters of torque. Okay. So we just calculated that. That's the torque caused by the force. So the force caused the torque. Next thing we want to know is, remember, we have the formula here, right here, is tau equals IA. So we're looking for A, or alpha, but we know T, but we don't know I. So what you'd have to do is, you have a disk, and you'd have to figure out, like, using calculus. Like here, I'm starting out, and you'd have to integrate it across this radius, and yeah, you'd have to figure that out, what that is, using calculus. Of course, integral calculus, of course. But of course, there's just, for simple things like this, there's just like lookups that you can use. And so if you look it up in a textbook or whatever, you can find that the moment of inertia for a disk, a solid disk, which is what this is 1/2 mr squared. M being the mass, so half is half. The mass is the mass of this thing, which is 40 kilograms. 40. And then the radius is 0.2, right? 0.2 squared. And if you do all that math, you know it's 0.8. 0.8, okay? And so that is the moment of inertia. Okay, so if you know that, then remember, it's tau equals I alpha. And so all you have to do is divide by I, right? Get rid of that. And so alpha is just tau over I, right? So T is 6. So basically alpha is equal to tau over I, which is tau is 6 Newton meters, and I is 0.8. Therefore, alpha is 7.5 radians per second squared. Okay, so we got that. That's the other thing that we got. So that's alpha. That's alpha, which is great. Okay, now we need to know, so that's how many radians per second this thing is spinning at, which is good, but I don't know its velocity, right? And so what I could do, though, is I could just integrate this, right? Right. Remember, if you integrate acceleration, you find velocity. If you differentiate velocity, you find acceleration. But if you integrate acceleration, you get velocity. So if you just want to find the integral of this, right, it's just then you'll, right, if you do the integral of angular acceleration with respect to time, you'll get angular velocity, right? You're going to get angular velocity. So if you just integrate 7.5, it's just it's very simple, right? It's just 7.5 t. So omega, as a function of time, is, once again, you just integrate 7.5, which is 7.5 t, and then you'd have to enter in your initial conditions, which is like your initial speed or your velocity. And remember, it's at rest, so it's 0. So if you want, this is your initial condition, 0. Okay, so there we go. So now we have the formula for that. But t. So I'm trying to find the velocity here, but I don't know the time. What I can do is let's do this. So I can do this little guy here. We can do omega and time. And remember, the initial velocity is 0. Remember? And then we're gonna accelerate 7.5. That's the slope of this line. Okay, so at some time t, that's on the x-axis, and on the y-axis at that exact same point, it's 7.5 t. So we have t on the x-axis, and on the y-axis we have 7.5 t. Now the area under the curve represents how much we moved. So in linear motion, it would be meters, right? You moved 5 meters, 10 meters, etc. This is angular movement. So we're not talking about meters here, we're talking about angles, right? Degrees, radians, revolutions. And so that was already given to us. It says we went 0.2 here at the top, 0.2 revolutions. So we went 0.2 revolutions times 1 revolution is equal to what? 2 pi radians. And so if you do the math on that, you'll end up with 1.25 radians. That's how far we displaced. So, and that's out. So that's our theta. That's our theta. Is like degrees. Think of theta as like, how many degrees, how many revolutions, how many degrees did you go? Okay, so that's how far we went. 1.25 radians. Okay, so remember the curve. Whoops, right here. So this curve of this graph of omega versus time, the area under the curve, remember, is displacement. In this case here, it's not in meters, it's in radians, and we just got that. So this is 1.25. So this is just like you've probably seen in some of my other videos, this is a triangle, right? And all we have to do is figure out, we have to do some triangle math. So the area of a triangle is what? 1/2 times base times height. The area, we have it, it's 1.25 equals half. The base is t. The height is 7.5 t also. Okay, so we'll multiply this everything times 2. We'll get rid of that. And then 2 times 1.25 is 2.50. And then t times t, well, basically we'll have t squared, and this is 7.5. We'll just divide by that. And we'll take the square root of all that fun stuff. We'll have t, and then we'll end up at 0.57 seconds. So remember, it's moving. It moved 1.25 radians. Well, how long did it take to go to 1.25 radians? Well, it took 0.57 seconds. That's how long it took. So if you know that, then you can put that back in your formula. Remember, I had omega as a function of time is equal to 7.5 t plus 0, which we don't really need. So we're gonna put in omega at 0.57 seconds and do 0.57 seconds times 7.5, and we'll end up with 4.33, and this is our angular velocity, radians per second. So that's how fast we're going in radians per second at t equals 0.57 seconds. Okay, so our velocity at that time is that. Okay, great. So now we basically have almost everything we need. So if I want to find my tangential velocity, right? Velocity tangential. All I need is my omega, and I got to multiply it times my radius. That's it. How fast am I going? 4.33. 4.33. Remember, after 0.57 seconds. Times the radius, which I already have, 0.2, right? And that'll give me 0.86. 0.86. And this is in meters per second. So if this were a wheel, for example, like how fast is it hitting the ground, or how fast are we moving tangentially or linearly? So when we talk about velocity, we're now in the linear realm. Okay, so we're now moving. Let's say this is a wheel, and this wheel was attached to a car. The car would be going at 0.86 meters per second. So that's how fast it's moving against the ground. Great, and so we got that. Maybe I'll make that yellow, because why not? So that, let me make that black. Yeah, so this is my velocity. This is my tangential velocity. That's how fast we're going. Okay, that's how fast we're going. Okay. Now, I want to find my acceleration. So if you want to find acceleration tangential, remember that's the vector tangent to the circle, obviously. So remember, velocity is or omega times r. Acceleration is just alpha times r. Okay, because it's still at the wheel. Like you're still talking about the point that's touching the ground, and so you need to know how far out you're going, and so that's what the radius is for. So alpha, which we already had that, we calculated that, right? 7.5 radians per second. 7.5 radians per second squared, and then the radius is 0.2. And so you get 1.5 meters per second squared. So if this were a car, if the wheel were attached to a car, and you want to know how fast is the car accelerating, you'd say it's accelerating at 1.5 meters per second. That's acceleration tangential. Okay. All right. And then almost the last piece is the radial acceleration. That's the acceleration pointing towards the center of the circle. It's called radial acceleration. And it's a little trickier. It's just omega squared r. Okay, so instead of alpha, it's your velocity squared. It's your squared velocity. Well, it's your angular velocity squared. And we have omega. It's 4.33, right? 4.33, of course, squared times your r, which is 0.2. You do that, you get 3.74. 3.74 meters per second squared. Now this is directed toward the center of the circle, right? So if I were to draw this, here's a circle, right? So this is your radial acceleration radial. And then this right here is acceleration tangential, right? It's tangent to the circle. Or like how fast you're going, how fast the wheel is how fast it's hitting the ground. But if you want to find your overall acceleration, you have to put those two together, right? And do like this, for example, right? And create a triangle, right? Here's your triangle there. And so you have your two components. Remember Pythagorean's theorem, a squared a squared plus b squared equals c squared. Remember that? And if you want to find c, you get rid of that and just do the square root of that. And so that's what we're doing here. So you basically just take the tangential acceleration, square it, take the radial acceleration, square it, add them together, take the square root. It's just Pythagorean theorem. And then you can find the overall acceleration speed, like i.e. the length of this other arrow, okay? And if you do that, you'll end up with 4.02. So this guy is 4.02 meters per second squared. And that's not the tangential or radial, because those are just the components of the vector. That's the overall speed, or the length, if you will, of the acceleration. So anyway, I hope this was useful. Basically what we did, just in recap, is we took Newton's second law, F equals ma, and we sort of created an analogous version, torque equals, or tau equals IA. And so this is basically Newton's second law as it applies to rotational motion instead of like translational motion. Okay? And yeah, basically, and all the other things apply. You know, you're like, oh, I know acceleration, or I know alpha. Well, just take its, integrate it to find omega, or integrate omega to find theta, or differentiate theta to find omega, or differentiate omega to find alpha. Okay, so all the same things you learned before are still applicable. Except basically, instead of just using Latin letters like A, B, C, D, we're using Greek letters like alpha, beta, gamma, delta, etc. Okay, I think that's about it. See ya.